OK, so let's start with this second step. This is step 2. So remember what the power counting was. The collinear gluons had this scaling. The ultrasoft gluons have this scaling, which is the same as an ultrasoft momenta. And the right way of doing this kind of thing would be to take Feynman diagrams and do some matching calculations. But sometimes we're able to get away with just thinking about doing things by writing down field relations. And that's almost true here. When we were drawing our Feynman diagrams before, if you think about one gluon, this is certainly true. So if we drew Feynman diagrams before, we had this one, and we had this one, ultrasoft, collinear. And we just consider one at a time, so we could just think of adding them. And that's kind of almost true. It turns out that it's true up to some terms that we don't care about for the moment. OK, so but these terms are power suppressed. And we'll see where they come from later on. So the way you can think about this, if you ignore that complication, is that you really just divide the gauge field into two pieces. And there's one place that you've perhaps seen that before when you talk about a background gauge field. Right? You say you have a quantum field and the background field, and that's very nice if you go to background field gauge. And that's kind of physically what's going on here, because we have two different modes that have different wavelengths. These guys are really long wavelength. These guys are shorter wavelength. Remember that the p squared of these guys is much larger than the p squared of these guys. So this guy, and think about this formula in that way, that this is like a classical background field to the Cn and the A n mu, since the P ultrasoft squared had a scaling which was lambda to the fourth, lambda squared squared, and that's much smaller than P collinear squared, which was Q squared lambda squared. OK, so that's saying that this guy is much larger wavelength, a long wavelength mode to these short distance modes. OK, so we can think of this as a slowly varying classical background, and that's one way of thinking about this formula, and we'll exploit that a little bit later on as well. So now that we have the sum of them, we can just think about how big one is relative to the other, and actually the coefficient that's between them doesn't really matter too much for that. Well, so let's think about the power counting, which I already wrote on the board. So the power counting is that n bar at an is order lambda to 0, and so is much greater than the n bar dot a ultrasoft, which is order lambda squared. Same for a perp n, that's of order lambda. That's much greater than a perp ultrasoft. And so those two formulas mean that whenever I have a comparison between this and this, I can always drop the smaller one. And just like our momentum, there's one case where that's not true, where we have to keep both of them. And that's for the n dot a component. So here's something we can drop, n bar at a ultrasoft and a perp ultrasoft. That leading order can be dropped. OK, so that's what we're going to do in step 2. Step 3 step 3 corresponds to dropping a momentum relative to another momentum. So there was an expansion of the propagator in the case where we had an ultrasoft and collinear at the same time. And let's just write that down again, but let's keep the next order term. And I'll ignore the numerator, since just looking at the denominator will give us enough information for this discussion. We could do the numerator too. It would just lead to more terms. So there's some terms that I can expand into the, and then I get the propagator squared, or I get a p squared squared, because I expanded something in the denominator back into the numerator. So the next order term comes from a dot product in the perp momenta, because the p in perp is large. And so we get a term with 2 k ultrasoft dot p in perp that corrects the leading order term, and that's the first subleading term. So if you think about the power counting of these, this guy is lambda to the minus 2, and this guy is lambda to the minus 1. Okay, so there has to be something in the effective theory that at higher order will reproduce this second guy. So there will be some power suppressed Feynman rule in SET to reproduce the second term. So what that means is that you can't just think that you ignore this guy completely, this K ultrasoft perp. You might just say, well, I just set all the K ultrasoft perps and the K ultrasoft minuses to 0. And that would be something that you can get away with, if you're careful, at lowest order. But at subleading order, you can't. You need to think that they exist too. So whatever formalism we develop should not set them to 0. And that was one of my bullets, that we should think a little bit ahead. And this is me thinking ahead, that I'm not going to be able to just set those momentum exactly to 0. I'm going to need them when I start talking about subleading terms. Okay, so we won't set. So we expand. Just like we don't throw away the subleading gauge fields, because we will need those at subleading order as well. We neglect them in the leading order, but we have to sort of think that they exist still. And with momentum, it's a little different, since fields carry momenta. And so what you should think is that the fields are allowed to sort of carry these momentum, but the Feynman rules of the leading order theory are just not sensitive to them. And that's the right way of thinking. Okay, so what we need is an expansion of the theory that will do this, and that's called the multipole expansion. So let me remind you of some things about a multipole expansion. Well, multipole expansion you see in electromagnetism, remember? You look at a charge distribution far away, you see the total integral over that charge distribution, and then the dipole. That's the usual thing that you think of when you think of the words multipole expansion. You think of E and M. And it's similar here, except we're doing it for fields. So in position space, it's similar to this where we expand and we neglect some coordinates. So let me show you how a multipole expansion works in one dimension in position space. So let's consider the following. Consider an integral dx psi bar of x, a of 0, psi bar of psi of x. So one of the fields I stuck at 0. I expanded out the coordinate around 0, whereas the other ones I kept the x. Okay, let's see what this does for the momentum space by Fourier transforming it. So some momenta, some phases. And then some momentum space fields. And I just put 0 because I put one of the fields in the coordinate space at 0. Do the x integral. So I get a delta function that says P1 is equal to P2 because I didn't have anything in the k. And this is kind of along the lines of what we want. It says that the momentum P1 is equal to the momentum P2, and that's like expanding in k. So if we think about having some Feynman diagram where we have P1 and P2 and some k coming in, if we want in some component that P1 is equal to P2, then this is achieving that. Okay, so this is the analog of the kind of expanding in coordinates that you do in E and M. Expanding in the coordinates of a field is doing the same thing. It's giving a momentum conservation that ignores the momentum conjugate to that coordinate that I expand in. So what would the next order term look like? Still here in one dimension. If you think about the expansion, the next order term would be a term like this, then at x equals 0. Sorry. I don't really need dot since this is one dimension. So that would be the next term in a Taylor series of the field about x equals 0. And if you do the same thing, Fourier transform this guy, you can work out that you get the following. Okay, so the derivative here on the coordinate becomes a k, momentum. Because I should Fourier transform the field, then take the derivative, then set the coordinate to 0, so I can still get a k. And this x actually just ends up leading to a delta prime. You can write it as a derivative in momentum. X can be written as a derivative in momentum space, and then it's a derivative on the delta function. Okay, so that's what the second order term would look like. So if you were to think like this, you have some kind of Feynman rule that's proportional to a delta prime. And then how will you deal with a delta prime? If your Feynman rule had a delta prime, what you'd do is you'd integrate by parts, and then the delta prime would start taking derivatives of other things. So that is a possible route, but we're not going to take that route. We're going to do something simpler. So we could formulate the multipole expansion in position space like that, but we're actually going to formulate it in momentum space. So we're going to do the same thing, but we're going to do it in momentum space. What are some reasons to do that? Well, when you do Feynman diagrams, you do them in momentum space. So if we've already formulated things in momentum space, then we'll immediately get the Feynman rules we want to do loop integrals and stuff like that. So that's an advantage of the momentum space, is that you more directly get the Feynman rules you want and the diagrams in the form you want. It simplifies actually slightly the formulation, or somewhat, the formulation of gauge transformations. Which we'll talk about later on. And what I think is a nice kind of advantage is where the momentum expansion sits is in the propagator, not in the vertices. So we don't get Feynman rules with delta primes that we then have to integrate by parts to understand. We just immediately get insertions on propagators which would correspond to the derivatives that I would take from integrating that delta prime by parts. So this term that we saw before that looked like a propagator squared, which was we were sitting in momentum space, we expanded the propagator to second order. So we had this term that was k ultrasoft perp dot pn perp, and then it had this denominator that was squared. If you ask where in the effective theory is that, what is going to be the thing that corresponds to that, it's going to correspond to some collinear propagator with an insertion on it. And the insertion gives this numerator, and then I have two propagators, and that gives the two denominators. Okay, so that's how that term is going to come about. So there'll be some subleading Lagrangian that I could call L1 that I can insert on the propagator, and that would give rise to these terms that we were saying were higher order. OK, so we have to figure out how to do this. And I will just give a little bit of a picture for it today, and then we'll continue with it next time. So I'm going to have to back up a bit. So let's back up to the Lagrangian that we had before. And I want to just introduce us, since that wasn't we were not close to being done. We had sort of started down the path, but we weren't done yet. Let me give a slightly different name to this field. Let me put a hat on it. So I want to do the expansion in momentum space, so let me Fourier transform. So I'll call psi n twiddle of p the full Fourier transform of this guy, which was previously just a field x. And we'll think about doing expansions in this momentum space field. And for now, I'm also going to make one other simplification, and that is to only consider the quark part. And we'll put the antiquarks back in later. So if you like, we're considering sort of the A's and not the B's in the decomposition of the field. Okay, so let's think about this and think about how we can do an expansion that would correspond to this multipole expansion. And the analogy that I'm going to exploit here, although it's not perfect, is the expansion that we did in HQET. So in HQET, we said we had a full momentum for the B quark, and we split it into a piece which was kind of the big piece, and then we had a piece that was the small piece. And I'm going to do something similar in SET. I'm going to say I have a full momentum, move the indices up, that I'm going to split into two pieces because of the power counting. A big piece and a small piece. The big piece here will be the terms which were of order 1 or lambda. And then the rest here will be something that's of order lambda squared. And I allow that residual piece not just to be in the plus direction, but to be in any direction. Because remember, at subleading orders, I'm going to have to care about the other components as well. So let me just say that the residual could have order lambda squared pieces in any component. In the minus and the perp, I'm going to expand with these residuals being smaller than these terms here. And this momentum I'm going to call a label momentum, and this momentum I'm going to call a residual momentum. We'll see why that's a good language next time. But it's kind of connected to the idea that in the HQET, we labeled the fields by this V. And we're going to see that for at least some of the interactions, it's a reasonable way of thinking of these large momentum as just labels on the fields. OK, so we'll talk more about that next time. I think I don't want to go further with it. But basically, we're going to make an expansion in residuals being smaller than these guys. And in order to make that expansion, I have to have some notation for the different pieces. And we'll see where that leads us next time. It'll effectively lead us to the same thing as this multipole expansion in position space, but it's a little nicer, I claim. I like it a little more.